All right. So we have our formative from last week on Thursday that we are going to go over. And then we don't have too much else to do today. So if we take a look, it says that Galileo tries to measure the speed of light in 1683 with two lanterns. The plan was for him and his assistants to go up two hills at night, each with a hooded lantern. And Galileo would lift his hood, revealing the light, and start the lamp. And when his assistant saw the lamp, she would lift her hood to reveal her light. And then when the light got to Galileo, he would stop his timing. So we know that the two hills are, so we have two hills, and they are 2.4 kilometers apart. And so it asks, how long did it take for the light to travel from one hilltop to the other? So this one, we're not really using our waves calculations yet. We are using our wonderful kinematic calculations from way back in the beginning of the school year. So we're going to use the fact that we're looking for a time, and we know a couple of things. We know the distance between them is 2 kilometers, which means that it's really 2,400 meters. We know the speed of that light because it's light, which means that our velocity is going to be 3.00 times 10 to the 8th meters per second. And so we're looking for time. So we have a few equations we can choose from, but the one we should find out is that it's x equals x naught plus v naught t plus 1/2 at squared. Right. So this one right here, this 2,400 is going to be our x because that is our final distance. We have 3. And then we have our initial distance. What do we think our initial distance is going to be? Awesome. 0. Awesome. Our initial distance is 0. We're looking for time. We also need our acceleration. What's our acceleration going to be? Also 0, because our light has a constant speed, which means that it's going to stay the same the whole time, which means our acceleration is 0. It does not increase or decrease in speed over time. Which means we can cross out a couple things from this wonderful equation. We can cross out the x naught because that turns into 0. And this whole section over here with acceleration is also going to turn into 0. Which means if we wanted to rewrite this as a new equation, we would just have our x equals v naught times t. All right, if we plug in everything we know, we have 2,400 meters equals 3.00 times 10 to the 8th meters per second times time. And how are we going to get time by itself? Divide both sides by the velocity. So divide both sides by the 3.00 times 10 to the 8th power. And we'll figure out that time equals 0.00008 seconds, or 8 times 10 to the negative 6 seconds. Both are the same value. Any questions on 1A? All right, then 1B, it says if the light was a beautiful 580 nanometer yellow light or yellow color, what was the frequency of that light? So we're finding frequency, and we have the wavelength right here. This is our lambda, our wavelength. And we know one other thing. What else do we know about light in general? We know its velocity, which is what value? the 3.00 times 10 to the 8th meters per second. So we have our velocity, 3.00 times 10 to the 8th meters per second. We have our wavelength, which is 580 nanometers. And we want to find our frequency. We're going to use our wave speed equals wavelength times frequency equation. There is just one issue I have with those two variables that we already know. Does anybody see an issue with either of these?
Gotta convert it to meters.
We got to convert this to meters first because we have meters per second up here. We need meters down here. So if we're converting it to meters, we should know, or we should be able to figure out that it's going to be 580 times 10 to the negative 9 because it's 1/billionth of a meter. So we got to do times 10 to the negative 9 meters. Or you can write it as 0.12345 6 580. Both of those are the same value. Now we can plug them in. So now we can solve. So we're going to plug in our 3.00 times 10 to the 8th meters per second equals 580 times 10 to the negative 9 meters times the frequency. And how am I getting frequency by itself? Divide by which one? The wavelength. So we're going to divide both sides by the wavelength, and we should find out that our frequency is going to equal 5.2 times 10 to the 14th hertz, or 5.2 times 10 to the 14th, 1 over seconds. Any questions on 1B? All right, then 1C says, what are some problems they encountered that prevented them from successfully calculating that speed of light? Who could tell me a problem that they encountered?
The angle of the hill.
The angle of the hill, okay, so what if the hills are on angles and they're not standing right at the top? Awesome. What's another issue that they could have encountered?
Just the human reaction time.
Reaction time of humans, okay, so anybody in here able to measure to the 0.00008 seconds? Can anybody react that fast? Because I sure can't. And probably not Galileo either. That is a very small amount of time. There's a very short window that they're trying to get this to react in. And they are not going to be able to do that with human reaction time. It's going to take him too long for the light to get through into your eyes, and then for you to move your arm up to lift that hood, and then the opposite side do the same thing. And even just clicking the timer twice is going to take too long for him to do that. So reaction time of humans, what the hills look like, what's the temperature outside, maybe things are with weather are causing issues, they can't see very well. Lots of things could go wrong. The biggest one being that humans have slow reaction times, and you're not going to get to 8 times 10 to the negative 6 seconds. Just too fast for us to react in. Any questions on number 1C? All right, then it says for 1D that they realized they had a problem. They came together to discuss the next steps. How close together did they have to be so the sound wave time was the same as the time from part A. So this one is very similar to part A, is now we're trying to figure out the distance they have to be for that sound wave to travel with the same amount of time. So we're going to use the same equation from up above, and we are actually just going to take this one this time because it's going to be the exact same, because we know our velocity is going to stay constant for any wave, which means that we don't have acceleration. And since we are starting at wherever that first person's standing, the second person is going to be their final distance. We know that the initial distance will be 0. So we actually can just use this x equals v naught times t equation. And we're solving for our x, which means we need to have t and we need to have v. Do we have t or v? What's t? 8 times 10 to the negative 6 power. Awesome. And what is v going to be for this problem? 340 meters per second. So this time we're talking about sound, which means we're using the velocity of sound waves. So 340 meters per second. To figure out the distance that sound is going to need to travel for. So we solve this one, we have x equals 340 meters per second times 8 times 10 to the negative 6 seconds. Anybody tell me the value for x? How far is it going to travel?
Yeah, I got 2.72 millimeters.
Awesome. So we got 0.00272 meters or 2.72 millimeters. They are inches or millimeters away from each other's faces. They are right on top of each other. They got to be super, super close for that sound to travel at the same amount of time as the light did. Any questions on anything from question 1? All right, then question part B. So the second half of this one. First, let's talk about what kind of wave is this? Transverse or longitudinal wave? Is a transversal wave. Awesome. All right, and how do we know it's that kind of wave? How do we know it's not longitudinal? How do we know it's transverse? It's going up and down. Awesome. The wave moves up and down. So it's showing us that as we're moving up and down and the wave itself is moving to the right, we have those perpendicular waves to our motion, which means we have a transverse wave. Where are the nodes going to be on this wave? Where do I put the nodes? Awesome. Our nodes go on the dotted line right here. So these are our nodes. Then my antinodes are where? On the curve, on the peaks and on the troughs. So let's do a different color. So it's not red. Right here are antinodes. All right, if we have our nodes, we have our antinodes, we have our amplitude. Where's our amplitude?
It's the height of the wave.
Awesome, it's the height, we're right here. Do our amplitude. So we have 4 different spots for that one. Measure our amplitude. And last but not least, our wavelength. Where do we measure the wavelength? Awesome, so right between 2 curves, so we have our wavelength. We can measure it here, we can measure it here, or we can measure it from here to here. 3 different types of spots to measure our wavelength. All right, any questions so far? Then the last thing it asks us to do is draw a wave with double the frequency in blue and a wave with double the period in red. If we double our period, am I making twice as many waves or half the amount of waves? Or if I double my frequency, what does it mean to double our frequency? If frequency doubles, that means what else? What happened? The number of waves double. Awesome. We see twice as many waves per second. So we're going to see 2 waves for every 1 wave on our original graph. So something along those lines. And which means if our period doubles, do we see twice as many waves? Do we see 4 times as many waves? Half as many waves? A quarter of the amount? Half as many waves. So we had 2 full waves originally. Now we're only going to have 1. No, it looks a little messy. That's okay. And that was our entire formative. Do you have any questions on any of it? All right. Then the only other thing I have for you today, and it's the same assignment that you're going to have on Wednesday, is an EM web quest, so electromagnetic spectrum web quest. So you're going to learn about the different parts of the electromagnetic spectrum, including like visible light, ultraviolet light, infrared light, all that good stuff. Remembering that your summative is on waves is going to be on Thursday of this week. So also completing any missing assignments that you need to do. Reminder that on Wednesday is an e-learning day, which means it's a little different than normal Wednesdays because the teachers have meetings all day, which means there's no live Zoom meeting. So you guys are just working on Wednesday. But if you have questions, you can always send a message through Canvas or through email. Other than that, that's all I have for you guys today. You guys don't have to stay to work on the web quest, but if you have questions, let me know.